just to start, I will recall certain definitions and formulate certain conventional facts. So first of all, if we have a Riemann surface with matrix of B periods, capital B, this one, then its Riemann theta function is defined by this expansion. And I will not comment on Riemann theta function. I will better comment on theta functions with characteristics. Characteristic is a pair of two vectors, is a pair consisting of two vectors AB from G-dimensional real space, where G is a genus of our Riemann surface. And if AB are half integer, integer or half integer, they are called half periods. Theta function with a characteristic AB is defined via Riemann theta function, just by formula, from we know that Riemann theta function is quasi-periodic, which means that if we shift if we shift, sorry, okay, nobody else. If we shift its argument by an element of the lattice of A periods, it remains invariant, and if we shift by an element of lattice of B periods, it earns certain factor, and knowing this behavior, we can easily derive the behavior of theta functions with characteristics. It's like this. It's no more invariant under shift. Under shifts by the lattice of A periods. It earns very simple exponential factor, exponent of 2pi ATM, where upper T means here a transposition, so ATM is just a notation for the scalar product of A by M. Okay, and if we shift Z by the vector of the lattice of B periods, which is written as BM, then we have the quasi-periodic behavior written in the last line. Well, written in the last line. This everything is just to recall stuff and fix notation. Now, another important building block for our formula for solutions, which we are going to obtain, is prime form. Prime form is a kind of we define it as a tensor of as a tensor in two variables, p and q. Both p and q belong to our Riemann surface gamma. Let z and w be local coordinates, of those points. And omega 1 and so on, omega g, are basis holomorphic differentials. Then E of PQ is defined is defined also by explicit formula, which is written in the second line of this relation. What is what here?
Sorry, may I ask a question, please?
Yes.
What's the Russian for prime form?
Prime forma.
Так и есть.
Prime forma.
Thank you.
Okay. Well, so theta of nu is a theta function with characteristic nu, where nu is an odd characteristic, which means that the scalar product of its components, A and B, multiplied by 4, is equal to 1 modulo 2. Okay, and there is no matter which particular nu we will choose. A here stays for Abel transformation. Now, theta with lower I and j stay for partial derivatives in zi, zj, respectively. So E of PQ is defined. We can regard to E of PQ as to a tensor of weight minus 1/2 in Z and minus 1/2 in W, which means that if we make a change of coordinates, then certain change of coordinates, then say, let me write, maybe if z goes to if z equal to z of u and w equal to w of v, then say epsilon in coordinates z w goes to epsilon, or that means u v multiplied by z prime of u minus 1 over 2 v w prime of v minus 1 over 2. So we can regard to epsilon of PQ as to a quantity which depends not only on a pair of points, but also on the choice of local coordinates, and with a choice under a change of local coordinates, it transforms in this way. Well, it is a very important property of E of PQ E of PQ that it has a simple pole at P equal to Q. At P equal to Q. Just an immediate application of prime form is the following. Using theta functions and prime forms, we can give an explicit expression for any bipolar differential. What I mean by bipolar differential? I mean one form with two and only two poles with opposite residues at these points. For such differentials with such a differential with poles at PQ, we can give the following expression. It would be better if I would write the following on the left-hand side: omega of omega PQ of X is equal to what's written here. So X is a current point.
Sorry, Oleg, I missed what that EP of Q depends on characteristics. or not? Sorry, I missed.
It does not depend on characteristic. It does not depend on characteristic, and here, moreover, here in this formula for omega pq, we take just Riemann theta function.
Yes.
The only I will not check everything here, but at least I will tell what we should check. We should check the following. First of all, that it's that this expression is well defined. I mean, it's invariant under shifts by the lattice of periods. And for this purpose, we use known quasi-periodic behavior of theta. And okay, there is a certain quasi-periodic behavior of E, which I didn't tell anything about that.
Sorry, may I ask a question?
Yes.
So could you please remind me of the definition of AP? Sorry, I didn't know what AP is.
Sorry, AP, A of P?
Yeah.
Abel transformation. Okay, it's the following. It's the following. So P is a point of the Riemann surface. Omega 1 and so on. Omega G. Oh, sorry. Omega G are basis differentials. So this is Abel transformation A of P is equal to the following vector integral omega 1 from some point, some fixed point P0 to P, and so on. So it's considered since the path, since the integration path is defined only up to up to how to say these integrals are defined only up to
So what are the integral over closed loop, you mean?
Sorry?
So you mean so it's the Abel integration, right? Now
I haven't understood. Please repeat it. Say it again.
okay, so it's the Abel Jacobi map. Do you mean by that?
Okay. In Russian tradition, we call the map in this direction Abel map.
Okay, I see.
And
I
the
see. I understand.
inverse Jacobi.
Okay.
You
Oh,
see.
yeah. Sorry.
Due to there exist problem, Jacobi problem of inversion.
Okay.
You see, so
Yeah.
it's actually inversion problem due to Jacobi. So we are used to call only this map by Jacobi map, and this
Okay.
is Abel map or Abel transform or something like this.
Okay.
After we check that it's well-defined expression, it remains only notice that E of xp has a simple zero. What x of E of xp has a simple zero. I told wrong maybe earlier. E of PQ. It's written wrong here. Sorry. What's written here in violet color is wrong. E of PQ has a simple zero at P equal to Q. Has a simple zero, not pole. And for this reason, omega of PQ has two simple poles at x equal to P and x equal to Q. Well, so let me proceed. Now, it's also nowadays a standard, a kind of standard that if we have a Baker-Heiser function corresponding to having exponential having degree g non-special divisor of poles, where g is equal to the genus of the Riemann surface. So if we have a Baker-Heiser function with the degree g non-special divisor of poles and exponential singularities at n points p1 and so on pn, with polynomials qj of kj as exponents there. I mean exponents are as follows: E qj of kj by something, where kj is the inverse to local parameter, For such type of Baker-Hiller functions, there is the following theta function representation. What is what here? There is no question about, okay, theta here is Riemann theta function. A Abel transformation as earlier. Let me comment later on U upper J. First of all, let me tell that omega here is a unique meromorphic differential on gamma such that first asymptotically it's equal to locally and asymptotically it's equal to differential of the corresponding polynomial. I mean, at Pj with local parameter kj minus 1, omega kj has the following asymptotic behavior. And second, sorry. We normalize it by the condition which is written there, that A periods of omega are equal to 0. By these two conditions, the differential omega is uniquely determined, and then by U upper J, we denote its B periods, as it is written here. First of all, why it's this expression is well defined. Again, I will not check it now for two reasons. First reason is that Piotr Georgievich checked it last semester in slightly different situation. Second, it is nowadays a standard, a conventional matter, and for those who okay, and for those who still doesn't know the source for sources where it can be where it's written, I can give it later after lecture, maybe. Well,
may I ask a question?
Yes,
please?
yes.
I missed a point. So about N and G. G is the genus of gamma, yes. And,
Yes.
and is and N, is it connected to something or just
N.
yes?
N is the number of exponential singularities.
Yes, but is it arbitrary? So we Could we construct for an arbitrary number of exponential systems?
Yes, we can choose arbitrary number of singularities.
Okay.
And give their arbitrary polynomials of local parameter, I mean of inverse of local parameter. Yeah, and there is a unique meromorphic differential given by main part and principal parts dq of kg, and the condition of normalization that a periods of omega is equal to 0. So I do not check it now. Maybe I'll only comment that in order to you see, if we choose this integral, as I said, this integral is the integration path can be is determined only up to multiples of periods, well, only up to multiples of periods. For this reason, this exponent is defined only up to certain factors, and we but these factors are compensated by quasi-periodic behavior of the theta function, and as a result we have a well-defined expression here. Psi of p is well defined. Okay. Let me recall from the last lecture the following. What we need, so how to retrieve a solution to Euler type equation from spectral data. So we have our spectral data, a set, a Riemann surface, a set of endpoints, which are mutually different, local parameters in the neighborhoods of these points, and a degree g plus 1 minus g plus n minus 1 non-special divisor. By this data we obtain n Baker-Hieser functions. So in the last case we had only one up to normalization function, but the degree of the divisor was equal to genus. If we take the pole divisor of degree genus plus something plus n minus 1, we obtain actually n-dimensional space of Baker-Hieser functions satisfying all requirements, and by certain normalization, they are uniquely defined. And this normalization is the following, that if we take psi j near the point k, sorry, at the point ki, it is a certain exponential factor which I have written down many times already, and an expansion which starts from delta ij. So the function number j is singled out by the condition that at the point that this part, this bracket, has order, has zero order for I equal to j, and order +1 for I not equal to j. Well, okay, it's written here. It's actually written here. A matrix solution to the Euler equations is given by the, sorry, is given by the next term of the expansion, as it is written in the lowest relation. So the next term of expansion gives elements Vij, which form the matrix, which in turn is a solution of our equation. And it was just a preface. The lecture actually starts now, and our goal is to express this Vij via theta functions and prime form. Questions so far? Okay. Well, first of all, you see, we have the following collision. The solution actually comes from the Becker-Heiser functions with degree g plus n minus 1 pole divisor. And the theta function formula is applicable to Becker-Heiser functions with degree g pole divisors, and so we must some way to reduce the problem with g plus n minus 1 degree divisor to the problem with degree g divisor. And For this reason, we must make one more assumption, that there exists a meromorphic differential omega having second order poles at the points P1 and so on Pn, and only there. This relation for omega of P is nothing special. It only states that omega has second order pole. Okay. So we assume that there exists a meromorphic differential omega having second order poles at P1 and so on Pn, and which is important, having a zero divisor of the form d plus some d cross. Let me call this divisor d cross, not d plus. It's kind of more usual to tell d cross. Okay. Okay, and the statement is the following: if d is given, then omega and d plus are uniquely defined. They are determined by d, and this requirement of second order poles. Let me prove it. Let me introduce, let me invent a notation for local parameter zi equal to ki 2 minus 1. Then, near the point pi, we can rewrite the upper relation in this form, where where x is some xi here is some complex number. The only it's equal to residue of the form of the one form omega, and hence the only condition on the numbers x I is the following: their sum should be equal to 0 by the theorem on residues. Okay. So the residues it's well known that up to addition of a holomorphic differential, omega is completely given by its principal parts at the point at its poles, which means at principal parts at P1 and so on Pn. And these principal parts in turn are completely given by the numbers x, I, which satisfies this this condition. So there are n minus 1 independent parameters among them, n minus 1. And this sentence up to a holomorphic differential means that we can add any holomorphic differential which form G parametric family. G parameters come from holomorphic differential. In total, we obtain that omega is given by G plus n minus 1 parameters. But degree D is equal to G plus n minus 1, just by assumption about this differential, about this divisor. So we can fix omega by giving the divisor D. This is the claim of our lemma. For a given D, omega is uniquely defined. Hence, the remainder of its zeros is also determined, and this is just by definition the divisor D plus. So the divisor D plus is also determined by giving the D. Just in addition to this statement, we know that the degree of any the divisor of any meromorphic differential is equal to 2G minus 2. This is the degree of canonical class. On the other hand, we know that divisor of omega is written in the second line from the bottom here. Sorry. It's written on the slide in the second line from the bottom. That divisor of omega is D plus D cross minus double sum of PI's, because at every PI we have a second order pole. So letting the degrees of these two divisors to be equal, we obtain the following: 2G minus 2 is equal to G plus 1 minus G plus n minus 1, which is the degree of D, plus still unknown degree of D plus minus 2n, and n points here. And which gives that degree D plus is D cross is also G plus 1 plus n minus 1. Okay. Now we will move. We will step by step move to the theta function formula for V. first of all, okay. First we define a formally dual, a set of formally dual Baker-Heisler functions to the set psi j. What means formally dual? This means that their pole divisor is d plus, and exponential singularities are inverse to the exponential singularities of psi j. Is it clear? Or I should write down formulas. Okay.
Please do write.
Huh?
Please do write. I'm not
Should I write?
Yes, please.
Okay. Okay. So psi j, or better, psi I had the following expansion: exp, or better, e x I k I delta I j plus something at p I. Well, psi I cross, or better, psi j cross at, oh, sorry, nobody corrects me here. Kj xj kj, okay, at psi I at pj. Well, psi cross j at pi is equal e minus x I k I delta I j plus and so on at pi. You see, when I told about inverse exponential singularities, I only thought about this minus sign, okay? Lena?
Yes, clear.
Okay, good. And for this set of Baker-Heisler function, this set of Baker-Heisler functions has pole divisor d, and this one has pole divisor d cross, which is defined only due to assumption that there exists omega. Oh, sorry. There exists omega with all above conditions such that d plus d cross is its divisor of zeros. Well, so, oh, that's interesting. Sorry. Okay, this set of Becker-Hazer functions is called formally dual to the first set of Becker-Hazer functions. Okay, the functions with the cross are formally dual to functions without any cross. Well, just from definition, using known expansions for psi j cross psi I, okay, sorry, having these two sets of formally dual Becker-Hazer functions, we make from the single differential omega a matrix of differentials omega ij, just by multiplying omega by psi I and psi cross j. Well, it obviously follows from expansions that omega ij has this Vij as residues. Let me note the following. So omega has poles of the second order at P1 and so on, Pn. And zeros at D plus D cross. The product psi I psi cross j has this divisor as a pole divisor. Hence, zeros and in this product, zeros and poles contract, and this divisor is this differential is just holomorphic at the poles of psi I and psi j cross. It's holomorphic on the support of this divisor. Further on, omega ij has only two poles, only two poles at pi and pj. So it is a bipolar differential. It's a bipolar differential. Why? it's somehow clear. It's somehow clear because for the following, it's clear for the following reason: is if I is not equal to j, then either then for any k, not equal to I, j, we have the following. We have the following. The pole, sorry. Okay. We can forget this. If k is not equal to ij, then we have the following. Psi I is besides exponential part, its expansion starts from 0. At the point at pk, it starts from 0, and then the terms of order 1. Okay, is not good here. So for the reason psi j, psi I, and psi j cross have just zeros at all points except for pi and pj. This differential is just bipolar, and from expansion, it's completely clear that Vij can be is given just by residue of omega ij, say at the points pi, at the point pi. So we can read our solution just from the differential omega ij. Why it's better than read Vij from the expansion of psi j? Let's see. Let us see. Okay. Let's see. Consider dependence of the differentials omega ij from x, from x bar. Okay. First, take evaluation. Let psi be the evaluation of the Baker-Heiser function at the for 0 value of the x bar. Okay, this is denoted by psi I of 0p. Okay, then just divide psi j by psi j of arbitrary x bar by psi j of 0 and obtain the function phi j, or phi I is written here. Okay. And similarly, let's similarly define phi j cross. So it's just obvious that psi I of 0p, psi cross of 0p are just rational and just meromorphic. And hence psi I and psi j cross are functions with exponential singularities. They just inherit the exponential singularities. Phi's just inherit exponential singularities from psi and psi cross. It's also okay. So we can represent our differential psi ij in the form in this form phi I omega ij from 0 psi cross j. We in some sense we okay. In some sense, we so we singled out the bipolar differential omega ij in the middle here, but the profit we have is the following: phi upper I and phi cross lower j are already Baker-Heiser functions with degree g pole divisors. With degree g pole divisors. It follows like this. Both omega ij from x bar and omega ij from 0 are bipolar differentials. And for this reason, their divisor of zeros has degree 2g. A bipolar differential always has degree 2g divisor of zeros. It's just simple calculation. And so this differential in the middle has zero divisor of degree 2g, and the differential on the left-hand side also. So there is no other way, and both of them has the same two poles. There is no other way that phi upper I and phi cross lower j in general generically have pole divisors of degree g each one. And for this reason, the theta function formula is applicable to phi upper I, phi cross lower j. In opposite to Baker-Heather functions psi j, psi and psi cross j, to which it is not directly applicable. Well, now I have to explain final formulas. They look complicated, but my task is to explain that they are not complicated, and I will try to do this in the next 10 minutes. If I will not succeed, I will shift it to the next lecture. Well, as I explained earlier, the solution which is our goal actually is given by residue of the product is given by the residue of this product. Well, as I said, the theta function formula is applicable to phi upper I, psi cross lower j. And in the very beginning of the lecture, I also said that every bipolar differential can be expressed via theta functions and prime form like this. So what is written here are three formulas. The first is the theta function formula for phi upper I. The second is the same theta function formula, but written for psi cross lower j. And the third one is the formula for a bipolar differential via theta function, Riemann theta function, and prime form. Let me comment on some notation. Here, xk, uk is actually, you see, in the very beginning, there were b periods of the differential, b periods of this differential here on the place of this sum. There were periods of the differential of this differential. Okay. There were no no xk in the original formula, but here they appear. And omega k are just, omega k is a meromorphic differential with the second order pole at pk only. So we just express the differential omega introduced earlier. We express express it just via one pole differentials having poles of second order. Which are called differentials of second kind on the Riemann surface. Well, so okay. I would like to comment that lambda I and lambda J are just normalizing coefficients given up to a common factor, but I skipped. Unfortunately, I skipped it earlier, and it is not good time to explain it now. So let's skip it now. Okay. Just fix that there are certain coefficients here. Well, what we have to do is the following: to calculate this product and take its residue. It's nothing terrible. It's nothing terrible because when we multiply the first, so the first and the second exponents are just inverse, they contract and disappear. Alpha here, alpha upper I, alpha cross upper lower J are normalizing coefficients. I will comment on them a little bit later. Now, these two denominators, this one and this one, contract with the nominator in this expression. And what should we have in order to calculate a residue at the point pi? We just should notice that this expression E of pi has a simple zero when p is equal to pi. It has simple zero. So this is the factor which this is the reason of appearing a pole in this product. And in order to calculate residue, we just have to drop out this factor and let p to be equal to pi in the remainder. So the way to calculate the way to calculate this expression is easy. We just contract all these denominators and nominators, and in the remainder we let p equal to pi. Well, and this everything results in the first line on this slide. For example, this theta, the second theta factor, comes from psi cross, and the first theta factor comes from psi I. When we let p equal to pi, these two summands just disappear, and we have in remainder only this sum, which is written here. Now, there was a normalizing condition. On the functions phi I and phi j. And from these normalizing conditions, we, you see, let's return. This normalizing condition was as follows. Phi I, the non-exponential factor of psi I should start from unit at the point pi, but we are exactly at the point pi. So this gives the following normalizing, the following expression for normalizing coefficients. They are defined up to two inverse factors, gamma and gamma. Oh, sorry, and gamma minus 1 to minus 1. But what we are interested in is only a product of these two normalizing factors. So we have just theta of z0 squared divided by this more complicated theta factor, also squared. We plug it instead of product of alphas in this formula. The first theta factor in the denominator contracts with one of these two in the denominator, and finally we obtain finally we obtain this final formula for our solution via theta functions and prime form. So let me say that for the remainder of the course, it will be not this particular form of the solution, and this particular form of the solution will be of no importance. What is important is the way how we obtained it. This way is rather universal and is applicable also to Hitchin systems. So we have in remainder 3 lectures this semester, And my goal for these 3 lectures is to describe a Lux representation and Baker-Hazer functions for Hitchin system of type AN, which means corresponding to full linear group. I also will touch a little bit Hamiltonian theory. Just by the way, I guess I will be enforced to touch a little bit the Hamiltonian theory of Hitchin systems. So let me stop for today and ask for questions.
Yes, I have a question.
Yes.
Let us assume we have 2 Riemann surfaces that are diffeomorphic to each other. Can I renormalize the holomorphic differentials on one and on the other, respectively, that the Baker-Hazer functions will be the same or maybe the same up to a certain factor?
Riemann surfaces are diffeomorphic.
Yes.
So we okay, if they are diffeomorphic and marked points P1 and so on Pn are taken one set to another by this diffeomorphism,
Yes. And
then the answer is yes. And I even have a question: why should we differ between such Riemann surfaces? There is no difference.
That's the question I asked myself. Yes.
No, I'm sorry. I would like to, sorry, may I make a remark?
Yes, of course.
I don't like the word diffeomorphic, because assume that you have 2 complex tori. All complex tori are diffeomorphic, but we have modulus. They are diffeomorphic as real manifolds, but they are not equivalent as complex manifolds. You should be more precise, because they are different. As real manifolds, all surfaces of G are diffeomorphic. We have a huge group. But if you go to complex analysis, complex manifold, the transformation group is much smaller. I'm sorry.
Yes, I see. So
Yeah, you see, as the question was said, we should not, if to answer the question as it was said, then the answer is why. The answer is just a question: why should we differ between them? We should not.
But it means that they are not diffeomorphic in the holomorphic sense. They are holomorphically equivalent.
But Sasha, was this your question?
yes.
What you mean by diffeomorphic? Real diffeomorphic or complex diffeomorphic?
That's why I asked the question. I want to maybe to figure out what is the subtle definition.
Okay. Then sorry. In this context, there is so far no reason to discuss real diffeomorphic Riemann surfaces. We discuss only complex, algebraic complex curves, which means that they have complex structure.
No, because I'm sorry. Could I also repeat? Do you mind?
Okay.
If I do, you see my video? Sorry.
Yes.
Okay.
My camera. Yes, because, okay, very simple remark. I'm sorry, may I make a very simple remark? Because assume that you just, for example, you have two tori. This tori, you see, and you have this tori. This is this two tori.
I'm not sure everybody can see what you are drawing.
They are a little bit
Uh,
in the way of light. Yes.
Maybe you change the direction of light.
right.
Sorry, maybe you have, you mean now it's better?
Yeah, now it's better.
Yes, I see. So you have two tori. As a real object, they are diffeomorphic, you agree. But there is a following exercise. Maybe it's a good exercise from simple complex analysis. You have to annulate one annulus and another annulus. Could you prove that there is no holomorphic map from this to this one, which maps external border to external border and internal border to internal border? There is no holomorphic map if we have R1, R2, and we have R1, R2. You can holomorphically map this annulus to this annulus if and only if R2 to R1 is equal to R2 to R1. You understand? There is a good, I don't remember where I found, maybe in Shabbat book, but there is a good exercise. You can holomorphic, okay, you would like to consider holomorphic map. We would like to map external border to external border, internal border to internal border, and you would like to have one-to-one map, holomorphic. It's possible only if the two ratios are the same. Some good exercise from complex analysis. So these two tori are different as a complex manifolds, different complex, but they are, of course, diffeomorphic. I'm sorry. You understand it?
Okay.
Yes.
The question is the following. You understand that if you consider real analytic functions, you talk about diffeomorphism, you have huge infinite dimensional algebra. And if you have holomorphic functions, of course, you have much less freedom. You understand that, for example, another example, assume you have two-dimensional manifold or n-dimensional manifold. If you have, in a real case, you have infinite dimensional algebra of smooth functions on any manifold. But you can construct two-dimensional complex tori, of course. It's dim C is equal to, of course, real it will four-dimensional real dimensional complex manifold. It has no holomorphic meromorphic functions at all. You understand? Therefore, if you have two Riemann surfaces of the same genus, they're equal. Of course, they are diffeomorphic as real manifolds. It sounds very simple. And also, if you have any collection of points here, you can map to any collection of points here. Again, a simple exercise. You have infinite dimensional group and you can move almost everything to everything. The only parameter is genus. But if you consider holomorphic maps, you have modulus. The space of all cells of genus G depend on 3G minus 3 complex parameters. If G is greater than 1. G is greater than 1. But I consider to start with tori. These two tori are equivalent as real manifolds, but they are different complex manifolds. The proof, roughly speaking, follows from this exercise. You can map this annulus to this annulus, or if and only if this ratio are equal. Sorry, I wanted to make this remark.
Okay. Okay, good. Do we have any other question?
Yes, thank you. The remark was very useful.
Okay. Okay. So let's stop for today. Okay.
Okay.
And next time start from the lecture presentation for Hitchin systems. Okay. Goodbye.